Today, we're diving headfirst into one of the biggest challenges on the planet, building a quantum computer. You see, the promise of these machines is absolutely immense. But to build one, you basically have to go to war with the universe itself. It's a battle against the fundamental chaos and noise of the quantum realm.
So, yeah, let's just ask it straight up. Why is this so ridiculously difficult? What makes this a bigger beast than, say, building the supercomputers we already have? Well, the answer gets right to the heart of it all. Quantum information is unbelievably powerful, but it is also fragile beyond belief.
And this is our main villain. It's a process called quantum decoherence. Honestly, the best way to think about it is like static on an old radio. The tiniest vibration, a stray bit of heat, even just the act of observing a quantum bit, a qubit, can make it lose its special quantumness and just collapse. This is the noise that completely wrecks a quantum calculation.
Okay, so this noise problem, it is the single biggest hurdle standing between us and the quantum future we're all dreaming of. But here's the good news. Physicists and engineers are not just sitting around. They have come up with some seriously clever, almost sneaky strategies to fight back. And today, we're going to look at 3 of the big ones.
First up is a strategy called heralding. And the core idea is actually pretty simple. If you know you can't get a quantum operation to work perfectly every single time, what if you could just get a little signal, a little ding, that tells you exactly when it did work?
Right, so this is all about probability. Imagine a baker who knows that only some of their croissants come out absolutely perfect. With heralding, it's like a special bell rings only when a perfect croissant comes out of the oven. You just ignore all the burnt ones. In the quantum world, it works like this. You create a pair of entangled particles. You measure one of them, the idler. If that measurement is exactly what you want, it heralds that its entangled partner, the signal, is now in the perfect state you need. All the other attempts, you just toss them out.
And this isn't just a theory, it has real-world applications. Take a look at this device called quantum scissors. It uses this heralding technique to do something that people thought was impossible. Take a super delicate quantum state and amplify it without adding any extra noise. It uses a clever setup of detectors and mirrors that only lets the successfully amplified state through, announced by a very specific click pattern from the detectors. Pretty cool, right?
Now, our second strategy takes a totally different approach. If heralding is all about spotting the successes among a sea of failures, this next idea is about building a secret hideout, a place where the noise can't even find you.
And this really gets at the change in philosophy here. Heralding accepts that quantum mechanics is probabilistic. It works with the uncertainty. But our next strategy, called decoherence-free subspaces, or DFS, is all about working against the noise. The whole goal is to build a shield, a quantum bunker where your information can be kept safe.
So how in the world do you build a quantum-safe room? Well, a decoherence-free subspace is basically a super clever way of encoding your information so that from the outside, from the environment's point of view, all the quantum states look exactly the same. And if the environment can't tell the difference between a quantum 0 and a quantum 1, it can't mess with the information. One way they do this is with a technique called dynamic decoupling, where you're basically blasting the qubits with a sequence of really, really fast pulses. These pulses make the environmental noise just average itself out to 0. It's literally like putting a pair of noise-canceling headphones on your qubits.
Okay, but what if the noise is just unavoidable? What if, despite our best efforts to hide or get a herald, some errors still manage to creep in? Well, that brings us to our third strategy, quantum error mitigation. This isn't about avoiding errors anymore. This is about cleaning up the mess after the fact. Now, I know this circuit diagram looks complicated, but the idea behind it is just brilliant. Quantum error mitigation, or QEM, starts by actually studying and learning the specific noise patterns of a particular quantum computer, its own unique brand of static. Then, you run your computation over and over, but each time you strategically poke it, inserting extra operations that are designed to first amplify and then help you cancel out that very specific noise.
And the results? They are absolutely stunning. The red line on the graph shows the raw, noisy calculation. You can see it just goes completely off the rails pretty quickly. But the blue line, that's with QEM applied. It tracks incredibly close to the perfect, ideal answer. It's like having a digital sharpen filter, but for the results of a quantum computation.
This almost seems too good to be true, doesn't it? A way to digitally just erase errors from a quantum computer. And you know what? You'd be right to be a little suspicious, because this incredible power comes with a pretty significant catch.
And that cost is something called sampling overhead. What this graph is showing us is that as you add more qubits, as your computation gets bigger, the overhead, that gamma symbol, goes up and up and up. To get that beautifully clean result, you have to run your program many, many, many more times, and that costs you a whole lot of extra time and resources.
So, where does this all leave us? We've got these three totally different, really clever strategies for fighting back against quantum noise. But how do they all fit into the grand challenge? You know, the path to a perfect quantum computer.
Well, let's do a quick recap. Heralding is all about listening for that bell that tells you you've got a perfect quantum state. Decoherence-free subspaces are about putting on noise-canceling headphones to just block out the world. And quantum error mitigation is like using a digital sharpen filter in Photoshop to clean up your final result. Each one is an amazing tool. But, and this right here is the most important takeaway, none of these is the final answer. The research is really clear on this point. These techniques aren't scalable solutions for building the massive, universal quantum computers of the future. They are absolutely critical bridges that let us do real science on today's noisy machines. But the ultimate prize is still full-blown quantum error correction.
And that leaves us with this final, really fascinating question. We know these techniques might not be the final destination, but just how much can they help us along the way? Can we maybe combine them in clever ways to make that incredibly long and difficult road to a truly fault-tolerant quantum computer just a little bit shorter? A little more efficient? Honestly, that is the billion-dollar question that researchers are trying to answer right now.